Welcome back. So, yes. How are you doing in terms of light? Is that good if it's closed or do you want it open? It's okay, this? Or maybe like this. So, welcome back. Last time we discussed the toric code, and then in the end of the lecture also discussed the toric code coupled to fermions. So, these are the terms that are appearing in the Hamiltonian. This is, as in the usual toric code, the flux term, product of all z operators around the packet. Z and x capital letters are just Pauli operators, and they're living on a bond. The Q operator is the one that in the Z2 gauge theory is strictly enforced, corresponding to the Gauss law. Here it's enforced only energetically. So when H is positive, Q wants to be 1. And it has the product of all x's around a given site. And in this case, with the fermions, also the fermionic parity. In the sense that, given that this is something like a Gauss law, fermions have a Z2 gauge charge.
Just to make sure, x and z is sigma x, sigma z.
That's right. And then there is a hopping term of fermions, and it knows about the configuration of the gauge field on the corresponding beam. So that's the same thing as final substitution, that's completely. And the important bit about this Hamiltonian is that, just in the case of the plane toric code, all q's and all b's are integrals of motion. So of course, all b's commute with themselves, so therefore with this term of the Hamiltonian. The b's also commute with the fermionic part of the Hamiltonian because it contains only z's. And then, as in the usual toric code, when you want to commute b's and q's, you commute at 2 links. You commute x's and z's, and you apply 2 minus signs to the whole thing. Also, the q's are integrals of motion. Well, they commute with the beta, they commute with themselves. They also commute with the fermionic term, because when you bring, let's say, this star here to this location, you will acquire a minus sign by passing this x through this z, but then the fermionic parity changes because of this fermionic annihilation operator. So therefore, all of the q's are also integrals of motion. This system is therefore nearly integrable in the sense that you can boil it down to solving free fermion problem. In particular, when k, it's called, we call it lambda here. When lambda is large as compared to w, both are positive, then we want that all b equals 1, all q equals 1 anyways. So what we do is we construct the ground state the same way that we constructed it for the usual toric code. We start by making all the b's happy, choose one gauge configuration, for example, all z's up. In this gauge configuration, it's easy to solve the fermionic Hamiltonian. So in this situation, it's just hopping on a square lattice. So you get some cosines in two directions, and this is the filled Fermi C. So you have, of course, your state live in the Hilbert space, which is both in the toric code sector and in the fermionic sector. And then to make the Q term happy, you just project this onto Q equals 1. Okay? This is, of course, again, a very entangled, free fermion state in the real space is also very entangled, but that's sort of trivial, it's just one state at a time. Here it's really a highly entangled state in the true sense of the word. It's essentially basis independent. Okay. I spoke about positive lambda. Today we also want to speak about negative lambda. So what we want to do is we want to do lambda much less than minus w, that's less than 0. What do we do then? So we do the same construction. Here. So when lambda is negative, the b's want to be -1 everywhere. Remember that b is infused, b squared to 1 and infused also squared to 1. So the eigenvalues are plus and minus 1. So all b's want to be -1 when lambda is negative. In that case, you have a pi flux everywhere. I show you this. How do you get a pi flux? So you need to have an odd number of spin down in a given plaquette. So for example, we can do it this way. See which way it shows. This way. Then we have downspin over here. And so now we have each plaquette, we have one downspin, and then all of the corresponding b's are negative. The Topological part. Again, let's think about first solving the problem without paying attention to this. We just choose a gauge configuration. This is a convenient one. We can discuss later that this thing actually does not really break translational symmetry, though it looks as if it was breaking translational symmetry. When you have fermions in a pi flux, you know what you get as a dispersion relation? Does anybody know this? No? So you get the Dirac. So first of all, it looks as if the grand zone was only half the size. In this case, this duplex zone. But this looks like the actual grand zone. You fold things back, and what you get is you get Dirac fermions here. So here you have Dirac fermions. You have a total of 2 Dirac fermions. You have 2 half Dirac fermions here and 2 half Dirac fermions here. So these are Dirac fermions. P, P, and these are Dirac fermions. Let's see, I'll show you some details about this. Okay, I do have some details here. If you want to see that, how you get Dirac fermions, then let's switch gauge, because I have somehow the notes that I have here, I have for vertical lines. So this is but of course it doesn't matter. Just so that when I copy things, more safe of the mistakes. So here this is the sign calculation, and let's assume we have Z bond equals -1 to the px. Right? So this is a different gauge, as I just said. This is a gauge where we have the minus signs on the vertical links. And then we choose a unit cell as which I saw. So this is the unit cell. You have 2, if you want to have 2 items in the unit cell. Okay. And then what we have is the Fourier transform on position x, 1. This integral small Baran zone d to the I k r k 1 equals k and c x 2 to k Brand zone. I, K, R, plus I, K, X, X, plus I, K, X, CK2. So this is shifted by 1. So the R position R is the position of the unit cell. And here we are shifted by 1 to the right. Yes?
Is the green line the line on the G axis?
Sorry, no. So the green line here is the same thing as here. So everything is hopping, is +1 everywhere here. So plus W here, plus or actually in this notation is minus W here, minus W here, plus W here. So this is the same thing as here. So let's go back what we did here. Apart from the fact that now I brought things by 90 degrees. We have here a configuration where all of the z's are +1 where it's red and -1 where it's green. That means that the hopping for the fermions looks as if it was +1, or actually minus, forget about this -1 here. It's the +1 here, and it's the -1 along here. So now I'm doing the same thing, solving this free fermion Hamiltonian. So wherever it's green, it's in this notation +W, and wherever it's black, it's -W. So what I have to do is I have to expand my unit cell so that I can solve the differential. And then what you get is, of course, you have hopping which is only inter-site. So actually, when you do the Fourier transform, you get this integral. Okay, so Fourier transform of this part here with the configuration of z's as described here. Small run zone. Now we have C dagger K1, C dagger K2 as a spinner. Same thing here. CK1, CK2. And you see this Hamiltonian is with only hopping between 1 and 2. So if I write this as a spinner with 1, 2 here and 1, 2 here, I have only off diagonal hopping terms. So we have minus, to just do the algebra, minus ky gamma z. Oh, did I write it wrong? Sorry. Here we have off diagonal. In y direction we have 1, 1. In y direction we have 1, 1. But in x direction we have 1, 2. So here we have gamma z. Gamma z because we have +1 here, or minus W in this case, plus W here. So we have different sign for hopping in y direction, hopping from 1 to 1. And in x direction, now it's really inter atom or inter object, inter subtype. The cos kx minus. So let me emphasize again that these green lines, they go in here. These are some polymatrices in this space, this 1, 2. And this one has relative signs compared to this one. And here we have, in x direction, we have polymatrices. And then when you take the dispersion, you take the dispersion relation, of course the energies are plus and minus. Square root, of course, there's 2W, 2W square root cos kx squared plus cos ky squared. And this guy will have zeros at pi half, right? So our Brand zone, originally it was going like this. This is minus pi, this is pi, minus pi, this is pi, minus pi, kx, ky. Now we've reduced the Brillouin zone because in this gauge we have double the unit cell in x direction, so we reduce the Brillouin zone in x direction by half. So the actual Brillouin zone is just this one, the one between the green lines. And as I said, this equals 0 for example, kx, ky equals pi half, because in the cosines both are 0, or also when you have different signs, plus minus. So there are here, there are points. When you expand there, you will see, the cosines have linear crossings to 0. When you expand, you will see that you get 0 points. So we can return now to this problem. Yeah.
Why you draw some parabolas like it would be there?
Parabolas. This, yeah?
Yes.
This was my attempt of drawing something three-dimensional. So let's see. What I was trying to do is
It's not KY, it's energy.
something like this. Yeah.
So it's Kx, Ky, and
Yeah,
energy.
so technically, that's what I was trying to do the axis like this.
Yeah, right.
Okay, so let's say from here. Yeah? Good. So now that we have solved this problem, so what we do is, as I said, so to solve this problem, which is at least looks much more complicated than this one, which is the free fermion problem. What we've done, we've first fixed the gauge to make this guy happy. To get a gauge, okay, it can be this one or we can choose this one, it doesn't matter. What we then do is, in this gauge, we solve the fermionic Hamiltonian. We get these 4 Dirac points. So far we have made this symmetry and this symmetry, and then we do the same thing as what we did before. We project it, let's say H is still positive, 1 plus 2r over 2, and that's the graph state. Yeah, so it's the same story as before. We can act with this Hamiltonian on this thing here, and the B term just commutes from here, and then will be evaluated in this configuration. The Q term anyway is happy because it's a projector. And the fermionic combi term, it commutes also through the Q, so I can just bring it here. I can evaluate all the Z's according to this configuration, and then I get actually just a hopping term of fermions, and then I evaluate it.
Sorry, once again, so is there a way easily to see that this is actually the ground state? I mean, each plaquette obviously should have one rotating spin. And,
so there is a condition that I showed here.
Yes.
So first of all, the H's, since the Q term commutes with everything here,
Yes.
as long as H is positive, this is the only, I mean, we have to have one Q. The question is about lambdas and W's. And indeed, it turns out that the situation is more complicated when the lambda is smaller than W. Because the fermions by themselves, they prefer certain gauge configurations. So I can give you a phase diagram for that. Looks like this. When you try to solve this function of density, you change this parameter lambda by W. Let's say this here is density, this is half filling, yeah? Half filling is here, here's 1, 0. When you have a half-filled fermion band, it is happier, let's say lambda is 0. Then it's actually happier to have this configuration than this one. And you can actually see it, because here you have a full fermion, see that you have a full filament. But here, in this case, you don't open a real gap, but you open something like a pseudo gap, you push more electrons below. So it's happier. The fermions are happier to have a pi-class configuration. That's a generic thing. So actually it turns out that there's a phase boundary which is somewhere order 1 on this side. So here, of course, here is that you want to have pi flux everywhere, you want to have 0 flux everywhere. So it's obvious that when lambda is very, very large as compared to W, the toric code part will determine what the B should be.
Okay, sorry, when you refer to pi plus or 0 plus, you mean in terms of?
This means it's the same as B equals -1, and it's the same as B.
Okay.
Yeah? And when the, remember, does she answer this question? I finished, yeah? So when lambda is very large, positive or negative, the toric code part will determine which flux configuration you have, and the determinants are set to follow. However, in this regime here, the determinants are the same. And as I said, so the determinants, once they prefer this one over that one, so it actually takes finite lambda to get across this. And this even depends on the filling. Actually, for situations it looks a little bit more complicated for fillings which are not a half. You get some intermediate regime which wants to have some flux configurations which are some fractions. But we can only do it on average because it's C2. So here in this regime it wants to have something like pi 0, pi 0, 0, something like this. So to have an average a half here. Anyways, what I want to say is that there is a difference between here.
How does it know that this is the same as for all projections? Right? Because we only did it for this configuration, but we have projections of all kinds of these bars.
I didn't understand the question. What projections of what? What is the same?
We have ground state, we computed the fermionic spectrum.
For this configuration only. Yeah, the logic behind it is the following. When you add the fermionic part of the Hamiltonian onto the ground state, you can commute it through this projector. And once it's commuted through the projector, you evaluate the z's. Once you evaluate the z's, you evaluate the c. Okay, so now you should be alarmed because we are at half, or we are at, let's say we are at half filling, so let's put it here, and half filling would be filling until here. And what you get is you get a situation where you have a Lagrange, König surface which is 0 essentially. Well, it should be half the Brillouin. This all in a situation where there is no translation symmetry breaking, and emphasize that this is just a gauge choice, and the system is still translation invariant in the sense that first of all we're cycling anyways over all possible gauge configurations. So when you just cycle here, you will get amongst others a situation where this is shifted as another contribution. And what I want to say essentially is that while this looks like breaking the symmetry, it's just a gauge choice, and if I shift in this direction, and I do a gauge transformation, I'm back at where I was. So it's not actually a translation symmetry breaking. So what we have is we have somehow a Fermi surface which is too small and appears to violate Lagrange theorem. That's essentially the theme of this chapter. Okay, let me go through what else I wanted to give comments on. Yeah. So the other thing is, neither of these states here breaks any symmetry, as I said. Both are topologically ordered, at least in the toric code sector. That's what we discussed, topological order. So how can this be so different? What I wanted to discuss briefly is different types of topological order. And for that part, actually, we don't even necessarily need the fermions, but they sort of help us understand this. Discussion of different types. So I should maybe highlight that you saw that we made this analogy to D2 gauge theories, and this is all very much related to D2 gauge theories, and or generally to gauge theories and deconfining phases of gauge theories. So it's no wonder that what we have to discuss essentially is different states taking into account the gauge group. So what we do essentially is, again, we classify, so what is done algebraically is to classify the crystalline symmetries of the system, taking into account that only these symmetries have to be represented only modulo gauge transformations. So as I said before, this configuration here, the pi flux configuration, if you just look at the pi's, it looks symmetric. If you look at the arrows, it looks as if it was breaking the symmetry in this direction. But that's only a gauge choice, right? And as I said, when you translate in this direction and you do a gauge transformation, you get back to where you were before. So that means we're looking at a representation of the translations modulo gauge transformations. So we are back to projective symmetry, projective representation of symmetries. Yeah? In this case, it's a phase, which is just plus or minus 1. Okay, so a reminder, projective symmetry, projective representation of symmetry, as we discussed before. So we have something like representation of G after H, something like e to the I, theta of GH, R of G, R of H. And here this theta comes because we have a gauge symmetry. Okay, so what we're looking at is translations, and in particular, in the usual case, with a representation of translations which goes like so. So when you shift the system, what we're doing is we're looking at shifts of the type, maybe I'm drawing this with you. We're looking at shifts of the system, where we're taking a system, we're shifting it by 1 like so, then we shift it by 1 like so, then we shift it back here, and then we shift it here, and we come back to where we were. This is the operation that we want to do when there's a difference here and here, because in this case, we enclose a flux pipe.
Sorry, what is K?
What is what?
For K, much bigger than W.
Oh, that's because I keep going to my other notation that's in the notes. I try to make things. So whenever you see K, remind me. Okay, so we do this. Okay, so this is actually a configuration where we first go up in Y, then we go to X, then we go down in Y, and then we go minus X. Reading from right to left. And in the case here, nothing happens, it's just the same as this way. Yeah. But let's do it for lambda less than minus W. Yeah, W always more. So shifts, shifts in Y with this case here are always supplemented with a minus 1, right? So Ty Y supplemented with minus 1x. Why do we do this? So what does this mean? Imagine we have our permanent parts, right? So if I shift by y, then I get a minus sign. Looks like I get a minus sign for the z part. And what I do now is on every other column, I do a configuration. This means what I do is I do C R goes to minus 1 to the x CR. It means that my hopping, my fermions get a minus sign on every other column, and thereby here or everywhere we get a minus sign for the hopping in this direction. So I get everywhere a minus sign here on these hoppings. So maybe I draw it just to see what this means. So when I do this, to this part here, that makes a hopping. So what this does here, since these are hoppings C dagger C, right? And on every other column I multiply the C to the minus 1. I get a minus 1 everywhere when I do this operation. Here because of this column, and here because of this column. But at the same time I have shifted so that I have, and of course I don't get minus signs in hopping in this direction, because both this and this gets minus signs. I had done this operation, which had changed here from minus to plus and here from plus to minus. So if I do both together, I get back to where I was. Agreed? So we're doing a gauge transformation of the C's at the same time as we're doing this shift. But then, so we have a representation which involves this. So we can do this. So we have the representation of the x inverse after representation of ty, representation of ty inverse, representation of x, representation of ty. These guys get extra minus signs. So we get we get essentially just tx, ty with a minus 1 to dx, tx, these are minus signs, tx minus 1 to dx, ty. So maybe I should color code. So this guy goes here, and this guy goes here. And these here just translation without thinking of the operation of, the representation of the minus 1 in the translation. And now you see that when you bring a minus 1 to dx across the tx, that gives you an overall minus 1. Because it shifts x to x plus 1. So then you have, here, when you bring the x, let's say, to the side, you get minus 1 to the x plus 1. The x is cancelled, but the plus 1 remains. So the whole thing is minus 1. This shouldn't look too unfamiliar. This is nothing but the mathematic translation algebra. But in this case, we have translation, we have flux pi, so the only flux you can acquire is the minus. Why did I do this? First of all, we see that these two guys are now, neither of those break symmetries, but they are of different topological order. So they are different states of matter. That's why we have a phase transition between them. And I also want to highlight that these different phases with different topological order, they are characterized by the projective representations of the crystalline symmetries. This is the simplest example where we look at translations. All right. So, yes.
Sorry. So after all, we found some kind of representation for the symmetry that we have in our system for any parameters, which shows different behavior in one set of parameters and the other.
So we have
say
different
that this is
representation.
different. Wait, but this is the same representation.
No, it's the same symmetry group, but
Yes.
the representation is different. Here we have a representation where we have to do something else to the fermions.
Okay. Okay.
But the symmetry group is the same.
Mm-hmm.
Everything is just a very random translation.
Yes, so sorry, I just want to formulate this like precisely. So we try to find some kind of symmetry under which we will see that different representations under different values of parameters, they will give us different behavior under the same group.
Yeah, same
Okay.
group,
Mhm.
different representation, different projective representation.
Okay.
And that's how we classify these different topological states. And this is because we essentially have this gauge group, so we have to do symmetry operations, modulo gauge transformations.
I don't really understand what exponent is.
Exponent x. This here. It means minus 1 to the, so x. So this is the lattice, and on the lattice we have positions r, which we call x and y. This is the vertices of the lattice. Okay. R is where the fermions live, and their position is called xy. Minus 1 to the x means minus 1 everywhere where x is odd, and plus 1 everywhere where x is even. So it means that, so I should write this here maybe more precisely. This is the function of x and position dependent x and y. Whenever x is odd, I get extra minus sign. When x is even, I don't. So it's a gauge transformation. It's a position dependent transformation.
May I also ask a question? So did I understand you right that for this transformation we basically we basically shifted the pi picture to 0 picture, applied the rule that along some contour we have to have unity, then expanded and realized that it's actually minus 1.
So I'm not sure where you said in the first time we sent a pi picture to 0 picture.
So when we apply this transformation, we say that CR goes to -1 to the power of CR. What we do is we change spins. Oh no, yeah.
Maybe it's a pretty stable, right? So there are two operations that we do. The blue one. So this is for this representation of C1, right? Representation of C1. And we do two things. We do the blue thing. And at the same time, what we do is, so the blue thing is from nothing to getting this -1 everywhere. Everywhere in this direction, here's +1, right?
Yeah.
And then what we also do is, we started out with the configurations where we had our green lines here, and now we ended up with the green lines here. Right? So we shift them up. Now you combine these. So this is at the end of this operation. This is at the end of this operation. You combine this with this here. Now you get additionally, we get in blue, the -1s that I acquired from here. So I get -1 everywhere. -1, -1, -1, -1, -1. Right? But that's nothing. It's the same thing as going simply with the -1s. That's exactly the same as this. Because now this green line will turn black again, and this black line will turn green again. So
That's why we have unity, and then as we expand, we see that it's minus on the one side and +1 on the other side.
but it has been fine throughout. That's when I'm
That's right. Yeah, that's what I meant. Thank you.
Okay. So now I wanted to get to Leibniz's theorem. So as I said, this here at half filling appears to violate Leibniz's theorem, which tells that in principle the size of your Fermi sea should cover half the Bremsel. And I also told you that this is of relevance for Coop rate research and also heavy fermion research, where it appears that certain quantum materials seem to violate the Leibniz bound.
Elio, one simple question. To understand the way that coupling, static coupling with fermions just may change the type of ground state simply because of different way to minimize error.
Absolutely. And ultimately, these are dynamic gauge fields, and they want to be either defined flux vector or zero. And then clearly you get a different fermion distribution. Okay. So, Leibniz's theorem, there are, I know of two ways of proving it. One way is a way that is field theoretical, involves some water identities, and you can find it in classic textbooks such as ADT or of the ladder, which is 9. And then there is another proof, which is topological in nature, and is the one that I'm going to present here. It's actually a generalization of Dichtschul's matrix theorem, which we might get to at the very end of the lecture course. And it's due to Oshikawa. It's very 2000s. That theorem is what, 60s or so. So Latinger Oshikawa theorem. Okay. So essentially what it does in words, the statement is the size of the Fermi surface is given by the fermionic density alone, independently of the strength of interactions, as long as there is no symmetry breaking. That's in words. What we are looking at is, we look at the square lattice. Which is Lx times Ly in size. And particle number n is n times Lx Ly, so it's density. And let's assume a Fermi liquid state, so as I said, all symmetries are preserved. We have a Fermi surface. You know, the main statement I think of Fermi liquid theory is that the low-lying excitations are still fermions with the same degrees of same quantum numbers as the free fermions. So this is the assumption. Fermi liquid state. That means no SFE. And then the theorem says, the volume of the Fermi surface in units of 4 pi squared is nothing but n over Lx Ly modulo, let me maybe restore the lattice constant is 1 over a squared. So this would be the lattice constant. And this here are the still bands. So obviously, if I have on a lattice, if I have like a system with like 5 bands, 3 of which are completely filled. I mean, I'm at half filling, 2.5 electrons per unit cell. But the lower 2 bands are completely filled, and only one band goes to the Fermi surface. Then the Fermi surface is just given by the band across the Fermi surface. Right? So that's what this modulo is. Yes.
Could you make it a bit more explicit what the assumption of Fermi liquid is?
So Fermi liquid means it's interacting fermions. They don't break any symmetry. So then, as a consequence, at least sufficiently high dimensions, like ours, the low-lying excitations close to the Fermi energy are still fermionic in nature. They are long-lived. Their lifetime diverges as you go to the Fermi energy. And their quantum numbers are the same as the quantum numbers of the original free fermions. That's the Fermi liquid.
VFS is the volume in the momentum space.
Yeah. Volume of Fermi surface in momentum space. So this has dimensions 1 over length squared, and this is 1 over length squared.
What's the question? When you said free fermions, you mean non-interacting fermions, not free fermions just as is?
What is the difference between free and undirected?
Free elements are elements that are in no potential, just electrons. Like,
Ah, I see. Yeah. No, because we're on the lattice, then there are only non-interacting elements.
all right.
So can you specify if this is letter W or?
There is no W, so probably you mean this N?
No.
This here?
No,
M?
in the numerator.
Yes, it's
Something divided by L.
Yeah.
No, something divided by X by
This one?
Yes. So this is the number of particles.
N.
Ah, this is the number of particles.
Okay, number of particles.
Okay.
So this is still N.
Ah, okay, great. And then N equals to what's formula N?
This is N times Lx Ly.
Okay.
This is little n, this is the same as little n.
Ah, this is the
So
same
it's
as
nothing but density.
Ah, okay, great. Okay, great.
Yeah.
That's I see.
Okay, so of course I'm not going to be super rigorous, but I'm giving you an system to prove by Oshikawa. Okay, so this is proof. So it's a flux insertion argument. So you consider a cylinder and you insert a flux into the cylinder. So let's do this. And so we have here a cylinder. On the cylinder we have our lattice. And so I'm trying again to draw this three-dimensional. Then what we're doing is we're inserting a flux. We're inserting a flux all the way through. That's fine. And we're ramping it up from 0 to 2 pi. Okay, so pi of t such that it's 0 if t equals minus infinity and 2 pi if t equals plus infinity. And what we're doing is we're going, so this is going to give a spin to this cylinder, and we're going to calculate the transfer momentum or angular momentum in two ways. And then we say it has to be the same. Let me emphasize that inserting a flux 2 pi at the end of this operation and at the beginning of the operation, the Hamiltonians are gauge equivalent. No gauge with respect to 2 pi usual U1. But the spectrum has reshuffled. I mean, the spectrum is the same, but the states have reshuffled. So it's a large gauge transformation. So we count this momentum. So let me just write here momentum transfer. Momentum transfer. Maybe you don't like the word momentum, so then it should be angular momentum. Okay, we're counting this momentum in two ways. Count momentum in two ways. So first, just electrodynamics. We have Faraday's law, so the force is just P dot. Maybe I write this here quickly. Faraday. What was the force? We call this in the x direction. This is x, and this here is y. At x is minus y dot over Lx. And then the total momentum that has been transferred is just delta p is momentum in x direction. This thing starts spinning, and it's just 2 pi Ly times density of particles which are charged with respect to U1. I mean, the particles which feel this field, the change of the flux at 0 and at 2 pi, that's just a flux and this is just a gauge transformation between having a flux 2 pi and flux 0. But as you crank up the field from 0 to 2 pi, that's when you have actual gauge fields. These actual gauge fields give you by Faraday law, they exert force on the fermions or on any charged particles in here. But in our case, it's just the fermions. And this force is given by, well, that's what's written there. So then you just use Newton's law for all of these charged particles. The factor of Ly is because there are Ly such layers. So it's extended in this direction. And that's what we get. The second way of calculating this, using low energy excitation. So that's more microscopic.
What is the physical meaning of E delta E? What is this one?
So this is the flux, this is the change of momentum before and after. So this thing, let's say in the beginning the cylinder is at rest, and now I crank up the flux from 0 to 2 pi. The cylinder, there will have been a force exerted onto the cylinder, just Faraday, and then this thing starts spinning. This is the total momentum after, just before and after. This means
I just multiply by M.
P, P after minus P before. And it's proportional to the number. This little n here is the density. So it knows about the density of the charged particles in this.
What is the transformation during this?
What's the answer?
When you say that we sort of flux.
So what we call a remove the Hamiltonian, I think. But what we do is we add a U1 vector potential to the Hamiltonian. And then this vector potential will be such that the flux that goes through the cylinder increases from 0 to 2 pi. So far our Hamiltonian had only the C2 vector potential.
So
It's an additional term in the Hamiltonian. Yeah. But if you wish, we can even forget about this. Is what I'm showing you now is independent of our model. You take any model of electrons, let's say, which have a U1 gauge charge, and let's say they're interacting, our model or something like this. You add by Pilot substitution a gauge field, and this gauge field you will let the phi times. Yeah?
So I do pilots.
Just imagine electrons which have a real gauge charge.
So you have reduction.
Yeah, okay, but
Your electrons does not rotate. Only the electrons that's not.
that's right. That's right.
Because I don't know rotating.
The signs, yes, that's right. So first of all, I should say, I've only coupled the electrons to the not the ions. Say that I would also add the ions. Let the ions feel the field. They also charge. And yes, but then that's for the second question whether you sort of relax. But you're right. The thing is, and I'm also, I'm only looking at the electrons. Thanks for highlighting this.
It's not relativistic.
It's not relativistic, yeah. But why is it important it's relativistic?
I have spin, I get zero energy.
Oh, I see. Okay, yes, and okay, fine.
So you're talking about
No, I'm just talking about
this charge is about.
Yeah, absolutely. Yeah. So it's important that I'm speaking about the electrons because I now want to consider only the low energy excitations of electrons. And as I said, we have a Fermi liquid, so for this field, let's consider a spherical Fermi surface. All the excitations that we know about, the Fermi liquid, we don't know what's happening deep in here or deep out here. These are excitations which decay sporadically. But we know the excitations which flows here. They are long-lived. And these are and since we have just a very small transfer here, whatever is carrying the momentum must be living close here. So maybe it's this thing becoming x. Yes. So everything is coming from here, from this little sliver. Okay, so the electrons acquire each electron or each quasi-particle acquires a small delta px, which is just 2 pi over Lx. Then we can calculate again delta p, maybe even in general for a delta vector. This is going to be in total the sum of all momenta, which I write as an integral and multiply with the volume of the system, n of p minus delta p minus n of p times p. So this is the momentum, the total momentum of the system, of the electronic part of the system before, and this is the same thing after, where they acquire this delta p. I expand minus y delta, in this case I think it's just delta x. Over 2 pi squared p px and p. I do one partial integral, bring this over, and then of course I just get only contribution in x direction. So I get total. So I use the delta p also that I had here, so 2 pi over Lx with Ly over 2 pi. And then once I've done this here, I just bring this over here. I get rid of this p here, it will just become px. Px being the unit vector in x direction. Then I just have to integrate over the distribution function, which gives me the volume of the König surface. Volume of the König sea. And I just have to evaluate, compare these two. So I compare this to this, and I end up here. You see this? Yeah, that's it, right? So we have the n here, which is this here. I bring this 2 pi I bring down here, and it's just you show me over 4 pi squared. This is the little n. And the modulo is actually coming from the fact that momentum on the lattice is conserved only modulo or reciprocal lattice vectors, and that gives it this extra unit of 1. Yes?
Where does the idea come from that we can do this using the solution?
Where this idea comes from? Is it a historical question? Or no, I don't understand the question.
So, why is it so to do this?
I still don't know how to answer this. I'm still trying to think whether I should come up with a way that people have started to think about this. I mean, based on the proof, you see, it's reasonable because you get information in 2 ways about what's happening to the system. Yeah, I don't know how to answer the question. There has been a previous proof for, which you might get to, which is a proof for, let me just tell you the history. There was, in the around 1990, there was a proof that spin 1/2 chains have to be gapless with a similar charge flux insertion argument. In that case, this is just spin, so they insert a very weird flux, which sort of changes only the wave function of the upper part of the spin. It's a flux insertion argument in spin space, not a physical gauge charge. And they were able to show this. Then, as I said, this problem of Fermi surface, I told you that this problem with the Fermi surface being too small appears both in the context of cuprates and heavy fermions. Heavy fermions, these are condylattice materials, so you have a spin sector and you have electrons underneath it. And they're coupled to each other. And sometimes you see a Fermi surface which is too small. Then Oshikawa came along and looked at the simplest generalization of the previously known model. The previously known model was a spin chain. So he added the electrons underneath the spin chain and repeated the arguments from the spin chain. That was still 1D. Then he went on to do it in 2D. Okay, I'm not sure if the historical answer is, but that's how it, I think, in the end came up that people started looking at these classes. Yeah.
Maybe it's a stupid question. I mean, Fermi surface is case P. Where's the mass?
No, the K, there's a difference. The difference between K and P is just H bar.
So you don't have an effect.
It's not about mass. I don't know. So P and K there is no mass, but in P and B there is mass. P is just H bar K. Right?
But will tell us where it is. So it's not that.
Yeah, that's a good question. So here, this does not assume anything about the cavity. It's just I have so and so many charges in here. This here assumes that there are low lying excitations and that they can shift the direction, which ultimately means that these are not localized. So to get this, so this side here, I assume that I have delocalized. Now, if you say localized, you mean mod or Anderson? Because this clearly does not assume, this clearly does not assume, so the translation is present. And now, if you want to start, let's say, like mod problem, indeed, this gives you constraints. So you cannot easily get rid of a filter. So a mod insulator, where you originally have a pump filling. So what do you do to get rid of this Fermi surface? One way is you break the symmetry, you have an antiferromagnet. Then all this doesn't hold anymore because we have reduced the overlap. Or the alternative is you have a spin liquid and then you have topological water. And you will see later, now, that the topological water is a loop-hole. I don't know, I think you were first.
I just have what does the x last time?
This means unit vector in x direction.
Where does it come from?
When I take, so here I took the full vector, but I kept only the shift in x direction. So I have only ddpx. I do a partial integral and I act on this vector p here, then I only get the vector in x.
So that is the state of the error sense of boundary conditions, like for periodic boundary conditions matter.
So this is definitely for the bulk system. Yeah. So you ask whether there is a similar theorem, or
So you assume periodic boundary conditions.
I do. I need this, right? At least in this direction. Maybe I should say that I've taken open boundary conditions in this direction. And the more accurate way of doing this is you insert first, you do essentially a whole torus. You first insert a flux this way, and then you insert the flux in the other way, and so on. But I thought I keep it simple, and this is essentially enough to get the gist of it.
How is the difference that if x is here?
And x is appeared from where?
From last year. On the right.
Here?
No.
Here? Here? Delta p is 2 pi r x and r.
Sorry.
And that's why I have only one 2 pi. Okay. So now we saw that we have in our model here, in this model, we had a situation where the Fermi surface was as it should. And then we also had a situation where the König surface was too small. Actually, at half filling, there was just no König surface. There were just 0 points that were in. So how is that possible? And this is this topological loophole in Lagrange's theorem. So you can satisfy this momentum balance if you have topological order. And essentially what's important are the anyons that we had encountered before, specifically the M particle, which is called Bison. So loophole. I'm not sure if the word loophole is very good because everything is, I mean, the Lagrange's theorem, it still holds. You just have to be more careful when you have the topological order. But if you think that the Lagrange's theorem just tells you that the B Fermi surface or B Fermi C is equal to the density always, then that's too easy of thinking of the Lagrange's theorem. In this case, it's going to be the Bison. So let's look at our problem that we had before. And what we're doing, however, now, so we start with our model where we had these lines on the lattice which were green, meaning that the hopping was on the ground state was sort of negative. So every other line is green. So black is equals 1, green is equals -1. Of course, keep in mind that we have the cycle of all gauge configurations, right? So I mean, this is only the starting state. And now, adiabatically, insert flux as before. However, slightly differently, 0 at t equals -infinity, but we only put pi into it. So that, well, okay, we get to this in a second. Yeah, so then again, the same momentum balance. Delta px is just pi times delta y. Obviously, if you insert flux pi into an arbitrary system, this does not map the system back to itself. We have changed this in a different configuration. But what we're doing essentially is we are absorbing this flux pi into our Z2 gauge fields. So essentially what happened is, after inserting the flux pi, we get essentially the same as before, but with a shifted configuration of minus signs. The lowest line. Inserting a flux pi means that as you go around the circle, you somewhere have to -1. And of course, to get this in the language of the excitations of the Tory code, by inserting this magnetic holonomy here, right? You have essentially the same thing. You have applied a string of x's on this line. So what I'm going to show you essentially is that this state, even if you don't do anything to the fermions, just the toric code sector satisfies, or sort of has the same delta P that we already found from the basic electrodynamic argumentation. So while here, in that upper case, we have absorbed, to have the momentum balance, we had to evoke the quasi-particles. We will now see that the boson, so ultimately just the toric code part, has absorbed this momentum that we have given to the system. And therefore there is no condition on the fermions. Okay, so what we've done is essentially flux pi in the C2H sector means that we essentially send H to magnetic autonomy, H magnetic autonomy at this particular position. And thus, our ground state that we had before goes to okay. So how do we see that this state here, even in the absence of a Fermi surface, carries this momentum? Okay, so first what we do is so what we're looking at essentially to study which momentum this state carries is we're trying to translate it and see what is the eigenvalue under translation. Remember that when you have a state and you translate it, you get e to the I, you have translation variance, so then you have eigenstates, any state, P, any state psi gives you some e to the I P psi if you have translation variance. Right? And we're doing this, we're trying to find what is the eigenvalue of restricted translation. So this is just a cycle mark. So to translate it, translate the state, translation, what we have to do is we multiply the q's. So what we want to do is we want to put here, we want to bring this over here, right? So what we have to do is we have to apply an x, which brings it here, x here, and an x here. And we do it everywhere with the q's. So what I'm doing is, let's say I want to bring this here. So I have to do x, x. But at the same time I want to bring this here, so I have to do x, x. And I can put here x, x, x. And then all of this here is already something like a star operator except for this fermionic current. And I do it here as well, so x squared here is 1, so that doesn't do anything. So again here a star operator, and again here a star operator. So I do a bunch of star operators next to it. But the ones, so here we have x, 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 x everywhere, but that's -1 to the r to r, so this is position r. So the translation.
Sorry, what is the state you act on? You actually on some kind of state.
This is just a reminder how to find out the momentum of the state. You just translate it, and you look at its eigenvalue under translation.
Yes.
This is a generic statement, so it's for arbitrary t.
Just in general.
This is just a general statement in case.
Yes. Okay.
And we are now translating this particular state and see what is it like under.
Yes.
Would it be correct to say that this loophole which we are discussing is actually the possibility to transform one ground state to a completely different ground state by inserting this house.
It's not a completely different ground. Well, it is a completely different ground in the sense that we now have this magnetic polynomial in it. That's right. Yes, if you wish, that's right. Yeah, okay, that's right. So, translation is like this. -1 to the, oh, sorry, this should be -1 to the nr. So, the Q was xxxx times fermionic parity. And the object that we're using here to translate is the object without the fermionic parity. So it's -1 to the r, and r, qr, acting on the ground state. And of course we do this everywhere along this line here. So this is all r's with x equals 0. Of course, by construction, we had the ground state which was an eigenstate of qr for any r. So it's just one. This is product for all r such that x equals 0, -1 the n in the ground state. The ground state is translational invariant. So the density operator can be replaced by its average. So what you get is the product over all r x equals 0 -1 to the density on the ground state, which you can of course write as e to the I pi average density Ly. So this thing here is called Ly in the ground state. So now we have to compare.
Sorry, may I ask a question?
Yes.
But just to clarify, so we are still talking about toric-code model.
So now we're talking about toric-code model.
Okay.
Here we did not.
Yes, for that was for any kind of system that have a fermionic frequency.
Yes.
Okay.
Toric-code, and in
Okay.
particular in the case lambda much less than -w. Less than 0. So we're interested in particular to see how our configuration that we had where the ledger account was manifestly violated, how in that case this is still consistent.
Mm-hmm.
And what we've done now is we've calculated the momentum that we've inserted in two ways. One of them is the standard way, and one of them is looking at this specific state and looking how it behaves in the translations. And what we find is that this momentum balance is always satisfied independently of the presence of a Fermi surface or not. So what we find, and maybe I write this underneath here, fine. Momentum balance is always satisfied. Balance satisfied. Bison. Or if you wish, one can generalize this expression over here. We have V Fermi surface over 4 pi squared equals, now in this case, is n plus 1/2 a squared modulo 1 over a squared. So even at half filling, we can have 0 Fermi surface. Yes.
This part is the Bison.
The Bison is the M particle. So It's the same. M and Y1 is the same. The notation, the word M particle is more common in the toric code sort of quantum information community. The word bison is more common in the spin liquid perspective. But anyways, it's the same.
Could you repeat this first time you write the translation?
Yes. Here, this here. So the translation operator, I want to translate the state. So I just have to act with this x, 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 x. We had defined the Q, which was x, 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 x times fermionic parity. So what I want to act on is -1 to the n times Q. So that's a translation. So I have to do it everywhere along this line. I call this line here, this was my direction x, right? So I call this here x equals 0. This line is the x equals 0 line. So I do it everywhere. Then I use that this is an eigenset of Q anyway. All Q on ground state per definition is the ground state. Then I use translation invariance and I replace this n here by its expectation. I say the densities are staying everywhere. Then it just says the whole product, right? The product was along this whole string, -1 to this number n, which I just write as e to the I pi n, and since I have this ly times x pi ly.
Is there a difference between the n and the first line and the second line?
Here and here, except that I remove the head, there is no difference.
Okay.
I've replaced it by, I said that the density is homogeneous, that's it.
I'm really sorry, completely missed the punchline. So,
Yeah.
we proved the Luttinger theorem.
So first of all, I
Yes.
that.
Okay, that was for everything. Then we get to toric code, and why doesn't it obey Luttinger theorem?
Because there is this topological order which gives you loop. So the whole point was the following.
And when you refer to loop code, what do you actually mean?
That it does not obey Luttinger's theorem.
That's it. Okay.
So we had solved the toric code in two limits.
Yes.
Lambda positive and large, lambda negative and large.
Mm-hmm.
In one case we had a big Fermi surface.
Yes.
In the other case we had no Fermi surface. In neither case we broke a symmetry.
Okay.
How is this possible following Luttinger's theorem?
Mm-hmm.
The answer is, first of all, we need to understand how Luttinger's theorem works.
Mm-hmm.
And the second step is, okay, let's now study the situation where we had this way too small Fermi surface. How does it happen? And the answer is, the momentum balance to derive the Luttinger's theorem is still fulfilled, but it's not fulfilled because of the fermions, it's fulfilled because of the bison.
Okay.
So if you wish, that's why I don't like the word loophole too much, because in principle, it's still consistent with the theorem.
Yes.
You have just to be more accurate.
Okay. And once again, I'm really sorry, but Wisons, they are this elementary that string itself.
Yeah, exactly.
Okay.
Every particle
Mm-hmm.
equals bison.
Okay.
And that's what you get from applying this magnetic holonomies.
Yes, and this is just the string itself. That's okay.
The string that has split these guys here.
Okay.
And the last thing, you're just trying to show that the state and momentum exactly don't.
Here, I'm just showing that the momentum balance is fulfilled. Yeah.
And why is this like the lowest energy excitation? How to see it?
So here I don't use anything that is, why do I need to discuss what is the lowest energy excitation?
I mean, as far as we derive the second. Okay.
So I just said this is the ground state, and then I do something to the ground state, and I end up here, and then I show that there's the momentum balance is okay.
Okay. Okay.
That's all.
Okay.
There's no assumption that something is
Yes. Sorry.
Okay. So the last bit on this fermions in on the toric code, I wanted to discuss the fermionic Green's function. So it's also, apart from the fact that it's a simple model where you can see the Fermi surface reconstruction without symmetry breaking, it's also a simple model in which you can see essentially, well, you see the ideas of fractionalization and particle construction, or essentially of emergent gauge theories in the language that we've used so far. But you also see a Green's function which looks gapped similar to a Mott insulator. This is not really a Mott insulator, but at least on the single particle level it looks like a Mott insulator. So let's remind ourselves, so this is the Green's function of the, this was 5.4. Fermionic correlators. So let's switch, or it doesn't really matter, but let's switch to the case lambda positive, where our ground state was this, R plus R. So in the toric code sector, we had, in this case, a simpler situation where in the trial or the seed state, all spins are up. And then the Fermi surface is the large surface. And what we want to calculate is Fermi Green's function. Just expectation value, time ordered. Cx now, C dagger, x prime now equals 0. Ground state. What is this? So what I do is I create a particle at fermion at time 0 at position x prime, somewhere here. And I want to annihilate it again at later time at the position maybe up here. That's fine. So what we do is when we act on the fermions here, we will just get a regular Green's function. However, the fermionic operation, the fermionic operator, does not commute with the Q. Remember that Q is -1 mr times product over all bonds around a given position. X bond. So the C anticommutes with this thing. What this implies is that at time 0 in position x prime, a Q is being flipped. And this is being unflipped at time tau at position x. So what we're doing is we're creating an E particle here at time 0. And we want to annihilate an E particle here at time tau. But E particles are not mobile. They're integrals of motion, right? In the toric code, E particles just stick to where they are. So what you actually get is this e to the minus 2h tau delta x prime g of the free fermion theory x prime tau. So in principle, the fermionic part tries to give you a Green's function, which is going to, that's the fermion move wherever it wants to move. So you create here a C dagger, so then it tries to go away, so it tries to go away. But at the same time, at time 0 at this position x prime, you also have to create an E particle. Let's create an E particle And E particles are gapped, they have an energy gap. In the context of this Euclidean time Green's function, this means exponential decay with the energy gap. This was the energy gap of the E particle. Remember, each E particle costs energy 2h above the ground state. Moreover, the E particle has to stick where it is, so it has to come back where it came from. Even if the fermion tried to explore the whole system. When you Fourier transform this, you Fourier transform and then you analytically continue to get the retarded Green's function. And try to calculate the spectral weight, imaginary part of the Green's function, retarded Green's function of omega. And you can plot the spectral weight as a function of momentum. This Green's function is ultra-local because the E particle couldn't move anywhere. So the Green's function is only a finite number when x and x prime are the same. That means that when you Fourier transform it, it means it's completely flat. Moreover, so it will be the imaginary part of the spectral weight here will be completely k-independent. And moreover, there is this gap that it costs to create an E particle. Despite the fact that the fermions are gapless, E particle costs a finite energy. So therefore, if you take this Green's function, Fourier transform, and analytically continue, you get spectral weight only above the energy 2h and below the energy minus 2h. And this looks very much reminiscent of Hubbard bands in modern insulators, where you also get some, so then this would look like U. It's not actually a mod insulator, but it's somewhat similar. Okay. Yes.
Sorry, and the correlation function, what is this? Is that J? Or what
This here, time ordering.
Time ordering.
I'm trying to write a calligraphic T.
Okay, and then what's the second Green's function on the next line?
This here?
Yeah,
This is the free Green's function of fermions with respect to this. Okay, this is just okay. So this is the full Green's function with this extra thing here. Means with respect to the full ground state as defined here. And this here is the Green's function evaluated with respect to this. So this one in blue can in principle go anywhere, standard Green's function. But then in the end it cannot because the E particles stick to where they are. Okay. This concludes everything that I wanted to say about Tory code and its generalization to fermions. Tomorrow we will start with field theory. Okay.